All right, chemistry, we're on to our next lesson, and this is a short lesson on additional facts of Lewis dot structures. So we're going to start off by drawing another Lewis dot structure, this one of hydrocyanic acid, HCN. So determine the total number of valence electrons. So you have 1 for hydrogen, you have 4 for carbon, and you have 5 for nitrogen. So you add those up, you get 10 valence electrons. So the HCN molecule has a total of 10 valence electrons, which must be placed in the molecule. All right, so draw the structure. Well, H cannot be in the middle. And carbon is a little less electronegative than nitrogen. So generally that's the way the formula is written the way it is, because that's the order of the atoms. So we're going to go ahead. H is 2.1, carbon's 2.5, and nitrogen's 3.0. H has the lowest electronegativity, but it cannot be a central atom because it can only bond on one side. Okay, this makes carbon the central atom. So that's going to be the structure. Okay, so connect the outside atoms with the central atom using single bonds. Okay, so there we go. So that's 4 of the 10 electrons right there. Now we have 4 of the 10. Okay, and then we create octets for all terminal atoms. Well, hydrogen already has an octet. So we create one around the nitrogen, and you can see that we've used 10 electrons, okay? So there we have all 10 electrons. However, carbon does not have an octet. So how do we give carbon an octet? So first you want to establish the number of electrons as 10. Now you got to arrange them so that everybody has an octet. So we're going to rearrange the lone pairs to create an octet for C. And there we go. And we do that by creating a triple bond between carbon and nitrogen. So now every atom there has an octet. So this fulfills the 2 requirements for a covalent bond. We used all 10 valence electrons, and we have created octets for all elements. The 6 electrons in the triple bond are counted for both carbon and nitrogen. So let's look at some exceptions to the octet rule. So elements in group 13, that's the column with boron, have only 6 valence electrons. So there is BH3, and you'll notice that it only has, boron has 3 valence electrons, hydrogen each has 1, so that's going to form an octet with only 6 electrons. If you look at the element below boron, that's aluminum trichloride, that's also going to have only 6 valence electrons for aluminum. The chlorines have 8, but the aluminum only has 6. So those are exceptions to the octet rule. Now let's talk about free radicals. You'll hear about those sometimes. The Lewis dot structure of nitrogen monoxide, NO, also known as nitric oxide, has 11 electrons. Okay, this results in a lone electron on the nitrogen. So that would be the structure of nitric oxide. Now the AP exam does not test on free radicals, but since you hear about them, I thought I'd include them in the lesson. So this configuration is called a free radical. Free radicals seek to attract another electron to complete the lone pair by stealing an electron from another molecule. Free radicals act as oxidants, to be discussed in later in the course, by stealing electrons, and that can be damaging to biological processes. Nonetheless, NO is advertised oftentimes for its health benefits. Generally, though, you'll hear about free radicals in kind of a negative sense. Okay, so how do we know whether a bond is covalent or ionic? We use the general rule that metal and non-metal forms an ionic bond and non-metal forms a covalent bond, but it's actually a continuum. We can have covalent, polar covalent, even more polar covalent, and then ionic. So there's generally a set of numbers that are used. So the following table gives a set of guidelines for classifying the 3 types of bonds. The classification of a bond can be determined by the electronegativity difference between 2 elements, as shown in the table below. So if there's a great electronegativity difference, say like between lithium and fluorine, which we know forms an ionic bond, well, fluorine has an electronegativity of 4, lithium has an electronegativity of 1. If you subtract those two, you get 3. So 3 is greater than 2, so that's definitely an ionic bond. If there's somewhat strong polarity difference between 0.5 and 2, that would be a polar covalent bond. And if there's very little electronegativity difference between the two, that would form a covalent bond, one that is nonpolar, and that's less than 0.5. So example, what type of bond does HCl form? H has an electronegativity of 2.1 and Cl has an electronegativity of 3.1. The electronegativity difference is 3.1 minus 2.1, which is 1.0. This means that HCl is a polar covalent bond. Okay, now this is something there's an 80% chance on the AP exam they will test you on this. It's called a potential energy well. Okay, so the bond length and energy in a bond between two covalently bonded molecules are displayed in the potential energy well diagram. The well diagram for two covalently bonded hydrogen atoms, that's an H2 molecule, is shown on the right. Chemical systems want to move to the lowest energy. So the lowest energy for an H2 bond is negative 432 kilojoules per mole. Again, that's a unit of energy. We'll talk about more in this class. This means that it would take positive 432 kilojoules per mole, that's energy going in, to break that bond, or basically to separate those two atoms. Now, also at that optimal energy, you can see that the distance between two hydrogen atoms is 74 picometers. Okay, so the downward slope to the right of 74 picometers means the atoms are attracted to each other. So as the two atoms are far apart, they're going to come together. And as they do, the energy becomes lower and lower and lower. That's a good thing if they want to bond together. So it gets lower and lower and lower until it gets to that optimal lowest point of 74 picometers. Then if you continue to go to the left, then the energy goes up. That means they're starting to repel each other. The protons in the nucleus are starting to push apart, and so it's not as stable. They don't want to be too close together. They don't want to be too far apart. So that 74 picometers, negative 432 kilojoules, is the optimal distance and energy for two hydrogen atoms. So the upward slope to the left of 74 picometers means the atoms are repelled because the electrons and protons are pushed too close together. Okay, so there's some facts you should know about bond length and bond strength. Single, double, and triple bonds have different lengths and different strengths, and this you should memorize. Single bonds are the longest and the weakest. Triple bonds are the shortest and the strongest. So let's look at some examples down here. Ethane is a single bond of two carbons, and there's the Lewis dot structure for it. They're using lines. You notice the bond length is 154 picometers, and the bond energy is 413 kilojoules per mole. Now let's go to a double bond. This is ethylene. So you can see that's a carbon-carbon double bond. The bond length is shorter, and it's also the bond energy is higher, so it's a stronger bond. Finally, we'll go to a triple bond, acetylene, and that's a triple bond between carbons. And you see that has the shortest bond length, but also the highest bond energy. So that's the shortest and the strongest, okay? So memorize that relationship among single, double, and triple bonds. All right, and that takes care of this lesson on some additional facts about Lewis dot structures.